It's a great pleasure to welcome Mary Sandoval from Trinity College, speaking on detecting orbifold singularities by the orbifold late spectra.
Thank you. And thank you to the organizers for the invitation. So yes, here's my talk, and I just want to emphasize that the spectra is not an accident. There's several length spectra that we're going to look at, or at least two, that we can associate to an orbifold. So let's see. Let's get going. So, oops, for some reason I cannot seem to. Oh, here we go. So this talk will address two questions. First question is asked, is it possible to detect the presence of orbifold singularities in a compact Riemannian orbifold via some length spectra, the length spectra of the orbifold, and another one that I'll be introducing. So the answer is a qualified yes. Everything depends on the dynamics of the geodesic flow with respect to the orbifold singularities, and we're going to see some interplay there that's kind of nice. So the tools here that we're going to use are some results from the theory of singular Riemannian foliations and some spectral results related to that setting. So let's proceed. The second question I'm going to address in this talk is, assuming the existence of a singularity on a closed geodesic, is it possible to detect aspects of the isotropy group? And we'll see that there are some partial answers there, and again, everything is always going to depend on how generous the dynamics of the geodesic flow are. So with respect to the singularity, so partial answers will be discussed, and as things go along, I keep getting more partial answers, but nothing really. Yeah, well, you'll see. So here's the basic outline. So I'll describe the two problems. I'll look at some background and look at a class of examples that'll be nice for us to sort of get our fingers on. I'll show the results to answer question one and a sketch of the proof, depending on how the time goes. And then I'll discuss the partial results to question two. So that's what we'll do. Oops, what's happening here? I seem to have skipped. Hold on. There's something odd here. I've skipped over many pages in the talk by accident. So let me just get back. Oh, here we go. Okay. So background, what do we mean here? An orbifold and its singularities. It's exactly what you expect if you've seen orbifolds before. Locally, an orbifold is just a mild generalization of a manifold modeled on orbifold charts, each of which is determined by a triple. As usual, you had G sub U, pi sub U, where U tilde is a connected open subset of D-dimensional Riemannian space. GU is a finite group acting effectively on U by diffeomorphisms, and pi sub U is a map from this connected open subset onto an open subset in the orbifold that induces a homeomorphism in the usual way. Let's see. So for each point in the orbifold, you can define the isotropy type of that point by fixing a lift p hat above your point in the orbifold and letting the isotropy group of p iso p tilde denote the isotropy subgroup G sub U at p tilde. It turns out everything's independent of choices, so we can actually denote that isotropy group by just isotropy iso of p. But in any case, for each gamma in the group, there we have a map D sub gamma p tilde in the endomorphism group of the tangent space that defines a linear orthogonal representation as a subgroup of the orthogonal group of dimension D. The subgroup is unique up to conjugacy, and everything's independent of all choices, as I mentioned. So we're just going to call that iso of p. So a point P in the orbifold is singular if that isotropy group is non-trivial. Otherwise, it's regular, and it's known that, of course, the set of regular points is open and dense. Okay, so let's talk about the length spectrum of an orbifold. The length spectrum of a compact Riemannian orbifold is just the set of periods of closed geodesics on the orbifold, which we denote by L spec of O. Okay. And how I'm going to do this is we have to think about how that geodesic arises. So a geodesic phi of t is closed with period t in O, if and only if one of two things happens. Its image phi tilde in the U tilde locally is smoothly closed at all points, okay, and phi prime of 0 is equal to phi prime of t. So that would just be a regular geodesic in the usual sense. But we could also have some geodesics of a second type that arise because they get closed up by isotropy. If it passes through if the geodesic passes through some singularity, it's possible that it's closed simply because of that isotropy and not because it would have been closed anyway. So in that case, we say there exists a P on the geodesic such that d gamma P tilde corrects basically the difference between the angles. So these tangent vectors to this curve are corrected by this thing so that the isotropy element for some non-identity gamma in the isotropy subgroup of P. Okay. Again, acting via the induced action on the tangent space. So if the second situation holds, there must have been a singularity on the curve. If all your closed geodesics avoid the singularities, then you're never going to see the second type. Okay. We're going to, without loss of generality, we're going to take P to be equal to gamma of 0 equal gamma T. Okay. So I should mention at this point, unlike the manifold case, it's not known if every compact orbifold has a closed geodesic, which is sometimes a little bit surprising. There are no known examples of a compact orbifold which lack a closed geodesic, but it's, as far as I can tell, it's still unknown. There's a little literature on it. I have some references at the end, but the situation, it's known that every compact Riemannian orbifold has a closed geodesic. If it's a bad orbifold, or if it's so any bad orbifold, the only ones that are not really known were that it's a very restrictive condition on the fundamental group. So there are no known examples of this, but I can pull up that reference and discuss it if there's time, if people are interested. So at the moment, as far as I know, based on preference in 2019, it's probably the case that every closed compact orbifold has a closed geodesic, but it's not yet known for sure. So so that's a little bit of an interesting fact. Okay, so let's just sort of look at a crude graphic to sort of understand the two types of ways we could close up a geodesic. And here, by U tilde, I really mean maybe a collection of such U tilde that cover a closed geodesic. So a smoothly closed one will always appear smoothly closed. We've got something down in the orbifold that looks closed. If I look at the lifts, it covers, you can imagine this is covered by a little family of U tildes, and it's just closed. And then we have the second type where we maybe have some singularity here, and we have what would look like normally a geodesic lasso, but this little angle here is going to be corrected by some element of isotropy at this singularity. Okay. Here I just have one singularity on the curve. There could be more. It makes no difference. The phenomenon we're interested in finding is a second type of closed geodesic, because if we have such a closed geodesic, then it has to have a singularity. So I call those closed but not smoothly closed. If I could find such a curve, again, that's equivalent to finding a singularity. And we'll see how we might approach this looking at length spectra. Okay, so I'm going to split up the length spectrum into L-spec 1, and this is going to denote the set of periods of closed geodesics for which there exists a smoothly closed geodesic. And then I have the second type, which is the complement of the other one. The goal here is to distinguish the second type from the first type. Okay, if we happen to have closed geodesics that have the same length as smoothly closed geodesics, well, we can't really tell those apart at this point. Okay, so maybe a good place to start is with a class of very good orbifolds. So this was something I hadn't heard of, but discovered in the literature. So a very good orbifold is a good orbifold where the manifold is actually compact to begin with. Okay, so you could look at quotients of spheres, very good orbifolds by if it's a good it's a good orbifold and it's something like a sphere. Sphere's compact, so that'd be a very good orbifold. If we had Rn and then we mod it out by lattice and we got an orbifold, that would not be a very good orbifold. And in this case, we know if I had a very good orbifold that any smoothly closed geodesic on M is still going to be smoothly closed once I quotient out by the smooth action, or the action of the finite group gamma. So in this case, we know that the orbifold will have at least one closed geodesic that it inherits from M, the cover. It's kind of natural to ask if there are more closed geodesics on O that occur just because of the presence of non-trivial isotropy. So in some sense, you would expect there to be maybe more closed geodesics in this case, because you have the ones that you had just by having a compact manifold, but maybe there are more ways to correct things. So you could have had geodesic lassos, which happen to close up smoothly or close up because of the presence of isotropy. So in this case, if that were to happen, then the length spectrum of M is going to be properly contained in the length spectrum of O. And so these are two spectra we can look at, two length spectra we can look at. And if we can detect the proper containment of one within the other, then we know we must have a singularity. Okay. So let's sort of lay things out here. Was there a question?
Yeah, actually, I have a question. Are you counting multiplicities in some way for the lengths?
No.
Oh, okay.
I'm not getting into the multiplicity of these things at all. I'm just seeing if there's, just look at the numbers, the lengths of these closed geodesics, and that's it.
Okay, thanks.
Could.
I have another question.
Yeah.
Do you have something else by assuming that gamma is cyclic in this very specific case?
There might be at the end. So you're assuming the isotropy is cyclic.
The group gamma.
Oh, gamma.
Cyclic.
If it's cyclic, I don't know. I mean, I'm not assuming anything right now.
Okay.
It's just finite.
Okay.
We could. I mean, we'll see that if it were cyclic, we'd expect to see certain things come up. But at the moment, I'm just taking a finite group gamma. Okay. So
can I ask another question? Sorry for the many interruptions. So it's not clear to me why you couldn't have a geodesic on on M, sorry, that sort of it's a twofold cover of a geodesic downstairs.
Oh, you could.
I mean, in that case, the length will be different, right? Or
you might get an extra. So you might get an extra geodesic after modding out, sure. But I think there would be a singularity on that geodesic, maybe.
okay, so this couldn't happen with a smooth one. I don't know. I'm just thinking. I don't know, the sphere and then project to space.
Yeah.
Maybe
So you should get. So if the original geodesic shortens up once you mod out by the group action. So then you get a new period. Okay. The old geodesic is still closed. So it double covers a geodesic downstairs, but that's still in the length spectrum.
All right.
An iterate.
Okay, thanks.
Of a smaller geodesic.
Right.
Yeah. Okay. So that would be what we'd be looking for. If it double covers, then we'd be happy because we pick up something new. Okay. So in any case, let's let sigma sub s denote the singular set of the orbifold, and then I'm going to look at a set Z, which denotes the set of points on the orbifold that lie on a closed geodesic. Okay, and we'd like to sort of investigate what happens here. So 3 cases. Suppose all the closed geodesics just never interact with the singularities. So the intersection of those 2 sets is 0. That would mean every closed geodesic avoids every singularity. And in that case, the length spectra are going to be the same for the manifold, that we're modding, the covering manifold, for the very good orbifold, and the orbifold itself. You get nothing new. And if you were to go and compute, say, the wave invariance, which is what I'd like to do, they would be identical for those 2 situations. So that's something we can't detect. If it's possible that the intersection of these sets are non-empty, but every closed geodesic is smoothly closed, so it's of the first type. So none of the geodesics close up because of isotropy. In that case, again, the length spectra are going to be the same. Okay. The wave invariance of M will be identical as well. So that, we can't detect that. The situation we're interested in is this last case, where the intersection of all the closed geodesics intersect with a singular set, and there exists a non-smoothly closed geodesic. And in that case, the length spectrum of M will be contained in the length spectrum, properly contained in the length spectrum of the orbifold. And that's what we'd like to sort of detect. So this is what you could do for a very good orbifold, but we want to generalize that. And so we'd like to see, for just a general orbifold, can we somehow get at the smoothly closed geodesics and compare them to, look at the length spectrum of M? We would need, in that case, something that acts like the covering manifold for this very good orbifold, and so we need another manifold lying around. And we have one. I'll get to that in a few minutes, but first let me just talk about maybe the length spectrum a little bit. So for a Riemannian manifold or an orbifold, we have Laplace operator acting on functions, and we have the spectrum of the orbifold. We have a wave trace, such as a generalized function on R whose singularities are contained in the length spectrum. So the length spectrum of O we think of as a spectral invariant. Okay. We can also think about one can also think about a d-dimensional orbifold as a global quotient. And this is what we need to do if we're going to look at geodesics, closed geodesics, because these closed geodesics will not necessarily lie conveniently in some local cover. So they may wander all over the manifold. So a global quotient is really convenient if we're thinking about closed geodesics. So in this case, old trick, we can look at the orthonormal frame bundle for an orbifold, and I'm going to call that M hat. And that's a manifold, and it's a compact manifold. It admits a global OD action whose orbit space is our orbifold. So the orbifold is the quotient by this orthogonal group of dimension D action. And you can think about the orbifold Laplacian on functions, and it's the OD invariant Laplacian on the frame bundle, the orthonormal frame bundle. And you can take a natural biinvariant metric, I think is the one we look at here. So the total metric on this space is just locally the product metric of the metric on the orbifold, and I call this G sub L. It's the metric on the leaves, because I'm about to introduce a foliation. But it is, you could just think about it as the metric on the orbits, or the orbits of this action. Okay. So the frame bundle is an example of a Riemannian foliation with the leaves given by the orbits for the natural action on the frame bundle. In fact, it's yields a regular Riemannian foliation, which means all the leaves have the same dimension, and the metric is said to be bundle-like. And the leaves are totally geodesic. And as such, it's sort of a special case of a singular Riemannian foliation. And I'm going to use some tools from that area, so that's why I mention it. The space of leaves is the orbifold O, and the functions on the frame bundle that are constant along those leaves are the basic functions, and those are just the lifts of functions from the orbifold itself. So the basic eigenfunctions yield a basic spectrum is what we call this. The basic spectrum of function is, well, it's the one associated to the basic eigenfunctions. And it gives us the spectrum of the orbifold, okay? But I could also think about it as the basic spectrum of on the frame bundle, where I take the foliation and the leaves of the orbits. Okay, turns out that's what we want to do. In this theory, there is a basic wave operator, a basic wave trace, a basic length spectrum. Been working on it for some time. I'll have the references there. The basic length spectrum is equal to the length spectrum of the orbifold, but it comes from looking at the lengths of periods of curves that are orthogonal to the orbits, whose tangent vectors can be related by isotropy. So there's a nice way of getting at these particular curves, and they're exactly the lengths of these curves are exactly the same as the ones that arise just by looking at the length spectrum on the orbifold. Okay, but I can think about them as curves that are up in this frame bundle. Okay. The frame bundle is a compact manifold, and its length spectrum does consist of smoothly closed curves. So if I look at the length spectrum of M hat, then those curves are smoothly closed. But they have a lot of curves in there that I don't want. So we'll see how I handle that in a minute. The length spectrum contains periods of lifts of smoothly closed curves from geodesics of O. So it does contain the ones that we're interested in. It also contains a lot of other stuff. But we can definitely say at this point that if we had a period in the length spectrum of O that was not in the length spectrum of the frame bundle, then that would have to be a non-smoothly closed geodesic. Okay. Unfortunately, that's not a great result because length spectrum of M contains a lot of stuff that we don't care about. Okay. So it contains periods of curves that are leaf-wise, by which I mean they're orbit-wise, or that are transverse but not orthogonal to the leaves. So it has a lot of stuff in there that I'm not interested in. So a result like this, finding a T in the length spectrum of O that's not in the length spectrum of M hat, this contains too much stuff. And so what I'd like to do is filter it out. So that's what we're going to do. So here's a theorem. It's quite useful in this situation. For every real number rho in between, in a non positive number, I can look at this metric here. I can essentially rescale the metric along the orbits by a constant. And that metric will be bundle-like on a bundle-like metric on M hat. And in fact, it defines an infinite one parameter family of metrics on M hat, which yield the same leaf space, which is our orbifold with the corresponding metric. And in fact, for this family of metrics, the basic spectrum is always the same, and it's equal to the spectrum of the orbifold. The key idea here is that the length spectrum of O is invariant under rescaling within this family, but the length spectrum of the frame bundle is not. So this rescaling is going to affect the lengths of any geodesic that is not, is of the type that we want to filter out. Okay. So here's a little lemma that's easy to show. L spectrum, the length spectrum of the smoothly closed orbifold, smoothly closed geodesics on the orbifold is just the intersection over all rho here. Okay. So anything that's smoothly closed will show up here. Okay, and if we have something that's not, then that's interesting. So said another way, if I have a T in the length spectrum of the frame bundle, and there exists a rho such that T is not in the length spectrum of the frame bundle with this rescaled metric, then the orbifold has a closed geodesic of length T that passes through at least one orbifold singularity. Okay. Maybe I'll leave that up for a second. So this is the way of getting at the smoothly closed geodesics. So if we find if we find a T in L spec of the orbifold and it happens to satisfy this criteria, then we know that it must be smoothly closed. Oops, we know that it's not smoothly closed, excuse me, and therefore that it has an orbifold singularity. So let me just check the time here so that I don't run over. I might abbreviate this section. So the proof here is pretty simple, and it just requires on two results from singular Riemannian foliations. Both of them need the notion of mean curvature, the mean curvature vector field. So let me just briefly review this. So the mean curvature vector field is a vector field that takes values in the normal space of the tangent space of the leaves of maximal dimension. For us, our singular Riemannian foliations are actually regular. So all the leaves have the same dimension, which is maximal. So this is not really an issue. And we get this operator, this mean curvature vector field H is defined such that H, we get the trace of the shape operator. Okay. We say that a vector field M is basic if it takes values in the normal space to the tangent space of the leaves, and the coefficients are basic functions. So when this happens, the mean vector field H projects to the quotient in a well-defined way. Okay. Furthermore, when H is basic, the spectrum, the basic spectrum is contained in the spectrum of the manifold itself. So here for us, this is M hat, the orthonormal frame bundle. Okay. So we should note that the basic spectrum can depend on the leafwise metrics, but that does not happen in this case. For the frame bundle, with a standard metric, H, the mean curvature vector field, is identically 0. The basic Laplacian is actually the orbifold Laplacian. Here's another result, and there are different versions of it. But whenever the mean curvature vector field H is basic, it actually works out to be the negative of the gradient of the log of the leaf volume. So L sub P here is the leaves. And remember, in this case, our leaves are just the orbits of the OD action. Okay. So this is stated very generally. And this is always a basic vector field for homogeneous singular Riemannian foliations. And in this case, if we rescale the orbit-wise metric or the leaf-wise metric by the constant rho, if you were to do that here, it's not going to change H at all, which is still 0. So when you rescale, of course, the metric, you're going to rescale the leaf volume by a different constant, but it's still just a constant. And when we compute H here, that constant gets hit by the gradient. We take the gradient and it's gone. So within the family of these metrics, the mean curvature vector field is constantly identically equal to 0. Okay, so that is convenient. The second ingredient in the proof is this result with Ian Adelstein and myself from a while back, and it simply says that when you have two singular Riemannian foliations, which in this case are regular, with mean curvature vector fields that are basic, and we have some phi here is not a geodesic anymore, but a metric space or an isometry, a smooth singular Riemannian foliation isometry. If H1 and H2 are both identically 0, then these two basic spectra are the same. Okay. for us, M1 and M2 are just the manifold here, the frame bundle, and H1 and H2 are 0. So this shows us that this gives us the fact that we have an isospectral family when I just simply rescale the orbit-wise metric in this way. Okay, so that's the result we're going to use here. The proof of the little lemma about the well, let me get back to it. The proof of the lemma concerning the characterization of L spec 1 as the intersection over rho in this family, that's straightforward. And with that, and this result here, we do get the theorem about the isospectral family. So that would show, so this lemma is straightforward. And with the results I've just discussed, then we get this isospectral family, which all have the same metric, the same spectrum, which is the spectrum of the orbifold. So these length spectra are all associated to the same orbifold, and that shows the result there, if we can get that. So that covers my first question. Maybe this is a good place to just take a breath and see if there are questions that people have before I dive into the second question. There's a little time check here.
Just quick question or comment. So I guess, is this a consequence of the Laplacian on the base being like the Laplacian upstairs plus a drift term coming from the curvature vector? There's some formula like that, right?
Exactly. So
Okay.
we're always getting, it's always associated to the orbifold because in this case, the difference between the G invariant Laplacian or the ON invariant Laplacian and the one downstairs is the curvature vector, mean curvature vector, and it's identically 0, all inside this family. So we're always getting the same thing. Okay, so let's talk about the second question. So the second question, if you recall, concerned, okay, so we can find a singularity in this case. What can we say about it now? So maybe you look at the geodesic flow, the length T geodesic flow, and you go and find the actual, you can find the geodesic that has a singularity with this particular period. What can we get anything out of that to say something about the isotropy group itself? And so that's what we'd like to know. We know we can't necessarily maybe determine the order of the isotropy because of other results by other people, but there is some things that we can say. Okay. And this is, as I explore this, I find I can say a little bit more. Everything is always going to depend in this case on the dynamics of the geodesic flow. So if that gives us a lot of information in a way that I'll discuss in a little bit, then we get more, but we can at least say the following. Okay. So we have a geodesic with singularity at P, and it's not smoothly closed. Okay. If the tangent vector of phi sub 0 is not equal to phi prime of T, then there exists some element of isotropy that rotates phi prime of T to phi prime of 0 in the two-dimensional subspace spanned by the vectors, those two vectors. So we know that there exists some element of isotropy that does exactly that rotation. If that angle between those two vectors is theta, and it's of the form theta equals 2 pi k times k over m, then m is going to divide the order of that isotropy element. And so hence it divides the size of the isotropy group. Okay, that's a little bit. We also could say that if it happens to smoothly close at this point, which we now know is a singularity, then there exists an element of the isotropy group which has eigenvalue equal to 1 and phi prime of 0 belongs to its one eigenspace. Okay. So we're assuming we've found the singularity, and maybe we have another geodesic that closes up smoothly there. This is what we could say. We could also, of course, look at iterates of that geodesic. Okay, so we're down in the orbifold. We keep traveling the same path. We don't know that it's always closing up corresponding to the same isotropy element. We just know that it keeps closing up by some isotropy element. But we could say the following. This is something that you do have to check. This involves a little checking, so it's not automatic. If I have a T in the length spectrum of O, then any multiple of that T is also in the length spectrum of O. I don't know that this closes up smoothly as I keep going around the same path downstairs. I don't know if it's closing up by the same element of isotropy or different elements of isotropy. But I can show that, as I keep traveling around the path downstairs, if I look up in the frame bundle, it's still closing up each time I go around, but maybe in a different way. So you can imagine we have a geodesic lasso the first time you go around, but then maybe the second time you travel the curve, it actually closes up smoothly, which is sort of a situation that I think someone asked about earlier. That could happen. Okay. Once it closes up smoothly, then you have something in the one eigenspace of an isotropy element. But we don't know, as we keep traveling around the same path, if it's giving you the same isotropy element or not. If we knew somehow that the isotropy was cyclic, well, then maybe, when we happen to have a generator, I don't know. It's a little unclear, but I just want to emphasize that as I keep traveling around iterates, I don't necessarily know that they're closing up because of the same isotropy element. Okay. But we can look at iterates, and we can look at the vectors, the tangent vectors to the geodesic, to get more information of the isotropy. But it's not yet clear enough that that's enough to determine the order of even one element of the isotropy of P. Unless, of course, the isotropy, it's size 2 or something very small. So it's a little bit of an open question here. Can we say more if some iterate of a non-smoothly closed geodesic becomes smoothly closed? And it's a little hard to say. We'd have to impose some conditions, maybe if we happen to know something already about the isotropy, but I kind of want to take the approach of, let's just say we don't know anything about the isotropy. Look at the geodesic, the dynamics of the geodesics, and see what happens. So here are some more sort of open questions we could look at. What if there's more than one closed geodesic that through this singularity that we found? Well, that would be sort of a case where the dynamics of the geodesic flow are very generous. And we could have multiple geodesics that are, independent, that are giving you more of a sense. So the more closed geodesics passing through P of any length that you have, the more information you're going to get about the isotropy. So, if you happen to be in a situation where you have a lot of closed geodesics through a singularity, then you're going to get more and more information about the isotropy at that point. Okay. So in other words, what if every geodesic through P is closed? At some point, you might be able to you might be able to totally determine an element of isotropy. It's not clear to me at this point yet, though. Someone asked about this. If you knew the isotropy was cyclic or abelian, then you would know quite a bit, because, well, then if you're looking for eigenvalues, if you're thinking about eigenvalues of the one eigenspace, then, well, then it's easier the situation when it's cyclic or abelian is easier. Here's a meatier open question, which is kind of what I would like to do sort of next, and I've been thinking about for a little while. what if we had some information about the Hamiltonian curves that projected geodesics? This turns out to be sort of a promising idea, and something I'll take a few minutes to explore in a little more detail. I apologize for the brick of text. I should have broken it up into some smaller slides. But let's go back to the case where we have a very good orbifold. Okay. There we can look at the cosphere bundle, which is a natural place to look at the dynamics of the geodesic flow. You can either look at the sphere bundle or the cosphere bundle, and for various reasons, I prefer the cosphere bundle. So in each case, you can look at these for the orbifold and the covering manifold in the very good orbifold case. The Hamiltonian flow you have there is the dual to the geodesic flow. And you can think about geodesic lassos that close up to be closed geodesics on O, which ones do and which ones don't. These are going to be Hamiltonian curves whose endpoints are covectors above P, such that there exists an element of isotropy that relates these two covectors. And I'm looking here at the induced action on the cotangent space. Correspond, it's just the appropriate dual thing to the one that happens on the tangent space. So here we could think about how the action of isotropy, the isotropy group is going to permute these elements, these points above, these covectors above the singularity. And there, maybe we can actually get some estimates on, or some lower bounds on the size of the isotropy in the following way. So we have these points, and didn't get a chance to make a better slide of this, but we have these points that lie above here. Isotropy permutes these endpoints that are getting identified. And what I'm looking at now is I suppose I know all about the geodesic flow through these points. Okay. Again, I can look at all possible iterates of a closed geodesic. They would connect different points above here, and I could, I have an infinite set of iterates, but I can look at the number of distinct endpoints that get covered. Maybe the geodesic flow doesn't pass through every such point that gets identified under the action, but it's going to pass through some of them. And this number of distinct elements that it passes through is a lower estimate on the orbit size. And of course, we're just looking at finite groups acting on a finite set. And so if I have the relationship that the size of the isotrope that orbits is equal to the size of the group divided by the size of the stabilizers. So if I had some sense of the size of the orbits, then I would again have a divisor of the isotropy group. It might be possible in some cases to assume that if, say, the isotropy were of prime order or something like that, that the stabilizers are trivial, in which case, again, we would at least say, okay, this thing is we have another divisor of the size of the isotropy. In any case, the idea here is that you can look at the interplay between the Hamiltonian flow, which presumably you can know about, and that's giving you information about the orbits of one of these covectors above P under the action of the isotropy. So there are things that you can know. Once again, if the Hamiltonian flow is sort of very rich, and we have a lot of different ways of getting at this set, how the possible endpoints of these curves, then we can know a lot. And so perhaps knowledge of the Hamiltonian flow will allow one to infer something more about the orbits. So this is what happens in the case of a very good orbifold. In the case of the more general case, there's something that plays the role of the cosphere bundle to M and the cosphere bundle to the orbifold. And that's something I've used previously in papers several years ago. But there's a nice space that plays these roles, and it's actually it's a subset of the cosphere bundle of the M hat, the orthonormal frame bundle, and that actually works out to be a very nice space. So if it sort of works out in the case of a very good orbifold, I can probably generalize it again in a very nice way with the same trick that I used before by looking at the orthonormal frame bundle. And so that's the idea. And I see that my talk is a little bit short, but I'll stop here and answer questions if people have them. Thank you.
Thank you, Mary. That's very interesting. Are there questions?
Not yet. I guess I'll just comment that the cosphere bundle, or excuse me, not the cosphere bundle, the frame bundle in this case is for people who study singular Riemannian foliations, is an example of a geometric resolution, meaning that well, it's a nice space to do work in, and the vectors, the curves that are orthogonal to the leaves are, they correspond precisely to the distances, the corresponding curves in the orbifold. So in the quotient. So it's kind of a natural space to work in.
So here's suppose you just look at something like footballs.
Okay. So quotients of a sphere?
Yeah. Maybe just say good footballs. Can you tell the order of the football of a good football?
So that would be a cyclic group, right?
Yeah.
I kind of feel like you should be able to. I feel like you should be able to, because it's cyclic. And you know, so it's abelian, and every geodesic. Well, are the geodesics through those spheres always closed? Is every geodesic through there closed? So we're talking a two-dimensional.
Yeah.
In 2 dimensions, you're just going to need. I feel like you could determine it because you're going to find an angle. Oh, but it could. Well, I guess you'd want to find the generator, right? You'd want to somehow know what happens. You'd want to figure out something closed under the generator, but I don't know how you identify which is the generator. I bet you could if it were prime.
Feels like it. Yeah.
It feels like it because if it's prime, then the stabilizers are trivial.
Mm-hmm.
I feel like you might be able to, and it's two-dimensional. So once you determine one angle, I think so I haven't, worked it out for any examples yet, but I feel like in 2 dimensions, you should be able to determine that angle. And if you've got the angle, then you've got the,
Mm-hmm.
well, I'm going to waffle a little bit. If it's prime, well, then everything is a generator, right?
Yeah.
If the isotropy is prime, everything generates. But you'd have to know that it was cyclic and prime. I suspect you'd have good luck there. And anyway, it's the sphere, so every geodesic is closed. Mm-hmm. So it seems like you should be able to, but I don't know for sure.
Okay.
But that's the sort of situation in which you have a lot of information already. But well, yeah, I worry about certain things. It seems likely. I'll say that. I should mention I have some references here. The first 2, by the way, are the two papers about closed geodesics on orbifolds. I haven't seen lately, I haven't checked lately if this first one is in print. That's the most recent one. The other one, the closed geodesics by Guru Prasad and Hefliger, is from 2006. But even in that paper, they could not determine if they had totally established that every compact orbifold has a closed geodesic. The restrictions on the fundamental group were severe, and there were no known examples. If you're interested in sort of understanding the Hamiltonian dynamics, that's gonna come out of this somewhat old paper as well. But there's a very nice space in which you can work, even for the frame bundle, for regular Riemannian foliation, which the frame bundle is, and you can do the dynamics very nicely in that case. So I have high hopes that it's extendable from the good orbifold case to the general case, using a lot of information there. And basically we have these endpoints, and they are the isotropy subgroup just permutes them. So the same thing should happen more generally as well in this nice space. Are there other questions?
We should just look at like flat orbifolds. So
Flat
for
orbifold, so you take a so is it very good or just regular?
actually, okay, yeah, actually, I'm not sure what my question is. I was thinking about how the Plough spectrum and the length spectra are equivalent for tori, but that's not true, I guess, even for Bieberbach manifolds. So I guess, yeah, as far as I know. So I guess, or at least I don't know that it is. I don't know.
Yeah.
So, yeah. I think I can't. I don't think I know what my question was. So that makes sense. Are there any other questions? Or well, thank you again for.
All right. Well, thank you for the invitation. Thank you.